So in the final section, we'll just look at what Fourier tells us about bandwidth of various signals. Now, so usually we'll consider that we start with an analog signal, but often we could also have digital signals, or we'll assume that we take an analog signal and turn it into something digital. And so we're looking what Fourier tells us about, if we have a digital signal, what its bandwidth might well be. So just to go back to our definitions, an analog signal we're assuming is something that's changing all the time, can change between any amplitude and can change at any time, whereas our digital signals are discontinuous pulses. So they have only given amplitude levels and they only change at set times. So if we assume that we have the fastest changing digital signal that we could have, that would be something that goes 0, 1, 0, 1, 0, 1, 0, 1, i.e. every time it has an opportunity to change, it changes between its states. And our bit period here is going to be this period t. So we know if we look at the frequency spectrum, we'll have a fundamental frequency, and that fundamental frequency is going to be given by now the period of our square wave. And we have to be a bit careful here in that our period of our square wave is not the same as our bit period. So maybe I should call this TB for a period of a bit, and we have big T, which is our period of our square wave, because our period of our square wave now covers both a 1 bit and a 0 bit, because that's how often it repeats. So compared to TB, our spectrum is going to look like this. Compared to the T as I drew it up here, it's going to look, this is going to be 1 on big T. And if I continue, we could put all of these in. So these are all now TB. And this shows us that we have a fundamental frequency that is at half the frequency of one of the bits, plus all its harmonics that make up its square wave. And so if we only had that fundamental frequency, then we would get a sine wave with a period that is 2 TB, 2-bit periods. Oops, just go to there for one period. So we could always approximate our square wave by using those sine waves, and that's what Fourier tells us, that we can always approximate it. So let's think about what that might mean if we use some of those approximations for a digital signal. So let's take an example. So this is some old school analog TV, the sort that's being switched off at the moment. So the UK system, a system called PAL, has 625 lines down the screen, and it sends 25 complete frames per second. Now that's something I just need to explain, because usually we talk about TV being at 50 Hertz. We send 50 frames, but what we're actually doing is we send every other line and then we fill in between and send the lines that are in between. Now this is a bit of a trick. There's something called persistence of vision. It's how often you need to change a picture to fool the eye to think that it's a fluid motion, and so you don't see the jerking between the picture. And it's somewhere between 30 and 40 Hertz you need to be able to do that. So TV plays a trick, so it doesn't have to send so much information. It actually sends a complete screen every 25, but actually at a 50 rate it sends half the screen, but it only sends every other line. And the gaps between the line are usually too small for the eye to be able to detect. So it looks like the whole screen is being updated at 50 frames a second, whereas actually it's only being updated at 25. We also have an aspect ratio of 4:3. And what that means is that if this is 625 lines down, the ratio between the short edge is 3:4. And so we can easily calculate what the width, the number of lines, the number of pixels across. So therefore, if we want to try and calculate the bandwidth that it takes to carry this signal, we need to work out what the number of pixels that make up the whole screen. How many values of pixel are we going to have to send? So if each line, if there's 625 lines and we know the ratio is 4:3, we can work out that across here there's got to be 833 pixels. And so fairly straightforwardly we can work out that one whole frame is going to be 520,000 pixels. So that's how many dots of colour make up the whole of this screen. Now we know we send a complete one of these 25 times a second, so that will tell us that there are going to be 13 million pixels roughly per second being transmitted. So you could work out that each pixel, so that's our TB, our time for each bit, each pixel of our signal, is going to be about 76.8 nanoseconds. And we know our fundamental frequency, therefore, is going to be 1 over 2t, or 1 over, carrying that on, 1 over 2 TB. And you could quite easily work out, I've got a typo there, that we should get 654 megahertz, which, you actually look at the bandwidth for an analog TV, is pretty much about right. That's the roughly the amount of bandwidth it takes to send this signal as an analog. Now what we're assuming here is that we only need to send this fundamental frequency. So we are approximating our square pulses of colour as a sinusoid. And for this particular case, that's a pretty good approximation, particularly as these also have levels within them. They're not actually ones and noughts, but they're pixels of different widths, different heights. So let me give you another example and ask you to take a look at this one as an exercise. We'll now switch over and imagine we sent high definition TV as an analog signal. Actually, we don't. We send it as digital and we compress it, but imagine we did. And so here we have our TV. We're going to have 1,152 lines, and our aspect ratio is now going to be widescreen. So the height is going to be a ratio of 9 to 16 between the height and the width. And this time we're actually going to go for a proper 50 Hertz frame rate. So I'm going to leave you with the answer of trying to work out what is the required bandwidth to send this signal if we sent it as an analog signal.